Okay, good morning again for yet another session for numerical methods. We are almost done with the semester. Last time we finished off with the initial value problem discretization. The lecture I had pre-recorded and shared with you contained the details of under the hood of what goes on within ODE integrate or ODE int, whether in Python or MATLAB. The ideas are the same. You take the time, you take the ODE, you take the time domain, discretize it into a number of points, and then you discretize that equation at each and every point because the equation is valid at each and every point, and then you formulate either a time advanced formula in an explicit integration or an implicit integration, and that allows, has pros and cons, etc. All of those good things. What goes on behind ODE int is far more complex, but it relies on forward Euler, backward Euler, and Craig-Nicholson, and all of those ideas are the basics of what goes on behind ODE int. Now we're going to look at the other type of ordinary differential equations that we have not talked about yet. Well, actually, we did talk about those early on in the semester with the heated rod and the tridiagonal system of equations, and I had told you at that point, if you remember, do not worry about how we derive those equations or that system of equations. Today you will learn how that system of equations was derived, and you have all the ingredients necessary to do just that. Okay, so with boundary value problems, you have a condition set on the boundary of your domain and a recipe or a formula or an equation of what happens inside that boundary. So you're only fixing the boundary and things happen inside the boundary. Contrast that to initial value problems where you only have one initial condition, okay, but you don't know where you're headed, what direction you're headed at, right? So that direction could be, at any point in time in the future, okay, depending on the formula, on the recipe, starting with the initial condition. With boundary value problems, the equation is bounded. So let's say you take the heated rod example that we're going to work with, or that represents, for example, your wall between the interior and the exterior. You're fixing the temperature on the interior, fixing the temperature on the exterior. That bounds what's going to happen in the temperature inside the wall. Okay, and we'll see how that happens. All right, so this is the classic example that I'm going to use to explain boundary value problems and how we solve them. It's the classic heated rod example, and I said you can consider your wall at your home as an example of a heated rod or just a heated section. Okay, you have a fixed temperature on one end and a fixed temperature on the other end, and there is heat being transferred because if those temperatures were different and the wall, what's going to happen over here, there's going to be heat that's being transferred from this side to that side or the other way around. Now, in this particular example, I'm taking also the heated rod, I'm blowing air over it. So think now of your heated rod, maybe your spatula, okay, immersed in cooking oil, for example, on one end, and there's like maybe a towel on the other end with wet water on it, fixing also the temperature at the other end, and it's hot, and you're cooling it with you have a fan that's blowing air at it at a T infinity. Anyway, the point is that the change in temperature along the rod, okay, spatially, not in time. We're not combining time and space. That becomes partial differential equations. But you can combine them, and in reality, that's what happens. But over here, we're thinking, at steady state, there's no change in time, only change in space. In this case, you're fixing the temperatures. This is the equation that describes how the heat varies, or the temperature specifically varies inside this rod. And I'm showing you here colors, red for hot and blue for cool, assuming that this temperature is higher than the other one. And you can see how the temperature of the air, T infinity, affects the right-hand side of this equation, okay? So based on the difference between the current temperature and T infinity, that is going to tell you what the second rate of change is, okay? And like I mentioned, the assumptions, etc. So H, P, and lambda and AC are just parameters, properties of the rod and the fluid that is cooling the rod. You don't have to worry about those right now. You will learn about how to derive this equation in your heat transfer class. But right now, take this equation at face value, and you're going to have to use the method that I described here in your heat transfer class to solve this equation in the future. Okay? All right, so the strategy we're going to learn about today to do boundary value problems is based on finite difference methods, which we also learn to use to discretize derivatives. Okay, so we're going to represent the rod is with this rectangle. We're going to fix the coordinates such that this location is x equals 0 and this location is x equal L. So the rod is of length L. We're going to fix the temperature on the left-hand side, and we're going to say this is T left, and the temperature on the right, we're going to fix that as T right. Now the thing to know here is that those two temperatures are known, and they are bounding, like there's an agreement between those temperatures and the heat transfer equation that, you know what, whatever you do inside the rod, the temperature always needs to go to T left and T right at the edges of the rod, okay? And now this is our equation. What I'm gonna do here, for simplicity, because I don't want you to worry about HP, lambda, and AC, I'm just gonna lump all of those into a coefficient H. I'm just gonna call it capital H for simplicity. Okay, you can change P is the rod's perimeter, and lambda is the heat transfer coefficient inside the rod. AC is the surface area of the rod. You know, don't worry about those. Just call this H and change play with the values of H. Okay. All right. So now we're going to start with some activities, and what I'm going to do here, we're going to switch to Zoom and do the activities on Zoom. There's like 4 or 5 of them back to back. Instead of switching back and forth, we'll just do all the activities in Zoom until we get to the bottom line. But we're going to try to figure out how to solve this equation together, okay? Specifically, you are going to try to figure this out yourselves. All right, so based on what we did with initial value problems, and specifically the lecture, last week's lecture, what is the first step in trying to solve this boundary value problem? You see the word BVP, that stands for boundary value problem, compared to IVP, which is initial value problem. Okay, what is the first step to solve this one numerically? I'll see you on Zoom, and we'll continue the discussion on Zoom, okay? Okay, I am here on Zoom, and I'm going to share my screen with you, and we're going to do these next few activities together. So just follow me on Zoom. Don't worry about YouTube. This will all be recorded on YouTube, however, in case you want to follow up later, okay? Let me just adjust a couple of things. Over here, okay, Zoom meeting. All right, do I have any takers?
I can give it a shot.
Go ahead.
So the first thing looks like we did with IVPs was to break it up into smaller pieces or discretize the data.
Correct. Does anyone disagree with Sarah? Nope. So we take the rod and just put discrete points, okay? And the purpose is to get ready to discretize the equation and convert it into discrete points, okay? So following up on Zoom right now, the first step, like Sarah said, is to discretize the space domain into n equally spaced points, okay? Now on the YouTube, you're gonna see this kind of in a shrunk, the slides are gonna be a little bit shrunk. Hold on, maybe Siri thought I was talking to her. Maybe because I said Sarah and it sounded like Siri. Okay, so we discretize the space domain into equally spaced points. Okay, and what I'm gonna do over here, hold on 1 second. And let's say that these, so the spacing doesn't have to be equal, but for simplicity, we're gonna make it equal as we move on in the discussion and assume the spacing is delta x between these points, okay? So now the next step was, like we did early on in the semester, is assign a coordinate value. I call this x, should be a coordinate value at each point. In this case, x1 equals 0, x2, x3, x2 is delta x, x3 is 2 delta x, and so on, all the way to xn equal L. And you can figure this out by with lin space or just doing, L over n minus 1, etc. That's not an issue. We know how to do this. Next, we're also going to assign a variable for the temperature value at each of those points. Now, we do not know the temperature values except for the value at the left and the value at the right, correct? So T1 is equal to T left. We know this is given to us, and Tn is equal to T right. And the remaining points, T2, T3, all the way to Tn minus 1 are unknown, or yet unknown, okay? Okay, great. Now this is our equation, d2t by dx squared is equal some coefficient into t minus t infinity. Now, the second question I have for you is the governing equation valid at these discrete points? Simple question.
Can I just clarify what the
Yes.
governing equation is? Is it the h times t minus t infinity?
Okay, that's only the right-hand side of the equation. That's one term in the equation. The equation, Sarah, is the full ODE. d2t by dx squared equal ht minus t infinity. Now remember, we moved from algebraic relations into differential equations now. And the differential equation relates the rate of change of the quantity of interest, which is temperature here, to something and to other things. Just like when we derive the compartment models, things are going in and things are leaving, etc. This is the same thing. Heat transfer just so happens that you can derive this equation d2t by dx squared by saying that the heat flux is proportional to the temperature gradient, and then the diffusion of that heat flux is the rate of change of the heat flux, so you get the second derivative. Those arguments you will learn to make later in heat transfer, but this is the full equation. d2t by dx squared is ht minus t infinity, okay? And when you say equation, you need to have an equal sign, right? You need to have an equal sign. Okay, who wants to take this?
I'm thinking that it is valid at the discrete points because it's almost like each point is its own boundary, like with what's between the points. No.
So you're partially right, but you it's like you volunteered information that is not necessarily needed. Okay, so yes,
Okay.
the equation is valid because the equation is valid over the entire rod, and therefore it is valid at any point inside the rod, however you choose it, right? That's the equation governing heat transfer. It is valid actually anywhere in the world, right? But for this specific rod, it is valid absolutely at each and every point, however you choose those points, right? Because that equation is continuous along the rod. Everywhere on the rod, this equation is valid. So it must be valid at the discrete points that you have chosen. All right. So therefore, at T2 at point 2, okay, then the equation is d2t by dx squared at point 2. Notice now the indexing, okay, that I'm using. Notice the indexing at 2. The second rate of change, the second derivative at point 2 is equal ht2 minus t infinity. Okay, pay attention to that. This equation, we're applying now the full governing equation at each of those points. And same thing, the second derivative at point 3 is equal ht3 minus t infinity. Okay, that should make sense to you. It's like applying an algebraic formula, e to the x. You apply it at any value of x. The same thing we're doing here, okay? Okay. So now that we know that the equation is valid, I hope this was, does anyone disagree with this?
I have a quick question.
Yes, Sam.
Are we making the assumption that it's like one-dimensional almost? Like if it had
It
multiple
is one
dimensions?
dimensional. We're not, yeah, that's been, yep. It is one dimensional. There's no, if you want to go to 2 dimensions, that becomes partial differential equations. And that's something beyond the scope of what we're going to do here. Not that you don't have the tool to it, but it becomes far more complicated. But yeah, it is one dimensional. There's no other dimension over here. Okay. Okay, now that the equation is valid at any point in the domain, we're going to take a representative point, point I, and say that just apply the equation over there. And I hope you agree that at that point, the governing equation is d2t by dx squared at point I. So you're evaluating the second derivative at point I equal h times ti minus t infinity. That's critical. It's at ti, okay? Now, based on what we did with initial value problems, what is the next step? Now that we know this equation is valid at each and every point, so on the right-hand side, remember we are after T2, T3, T4, we are after Ti, okay? So on the right-hand side of this equation, you see a Ti now. But on the left-hand side, you don't see a Ti yet, correct? You see a continuous derivative. So based on what we did with initial value problems, if you listen to last week's lecture, you should be able to tell what we're going to do next. Come on, you got 30 seconds. Let's see. I'm going to pick someone. I feel like I'm always picking the same people. I guess it's just the same crowd who shows up. Not too many, unfortunately. So, Sophia, do you want to take this?
I mean, I don't know how to do it, but I can look at it.
An idea, okay, do you have an idea of what to do next? Like, what are we going to do next? Okay, we have this equation. What's the next step? Just in words. Okay, let's see.
As in like,
yeah, go ahead.
no, just differentiating it or
so
beyond that?
How do you differentiate it? What does that mean? You don't have t. You can't differentiate it, right? So our goal is to find t2, t3, t4, all the way to tn minus 1, right? So we need a formula for those. And we only have the continuous differential equation. So how can we convert that continuous differential equation into a relation between those different temperatures? That's what I'm after. Okay, all of you, I know you know how to do this. And we did it twice so far with the initial value problems and early on in the semester. Okay, any other suggestions?
Can I take a stab at it? I would assume you would just do like a numerical derivative as
yes,
we did with
yes, great. Thank you, Porter. That's exactly what you were going to do. So when you think about this, you have this continuous equation. We are after a relation between the different points in the domain, so that because we don't know what those points are. So, if I were to think about this, I would say, okay, these are a bunch of unknowns. So, let's say you have T2, T3, let's say you have 100 unknowns, 100 T's inside the domain. To solve those, I need 100 equations. To solve for those, I'm going to need 100 equations because I don't have a formula for those. Okay, the only formula I have is a derivative. So then if I use finite difference, like Porter suggested, then we can untangle that derivative into a relation between neighboring points, right? Remember the finite difference derivatives? And once I have this relation, I can just apply it at each and every point. I will not have an answer. I will have the equation governing the answer, okay? So if we were to follow through with this, we just approximate the derivative. We say that d2t by dx squared is, fill in the blanks now, feel free to look up at your notes. What are we going to put in here for the second derivative? We're going to approximate the derivative with a relation that relates the points to each other. So look at your notes, go to the finite difference set of notes, and let's see what formula we can put in here. All right, let's see. Natalie S, do you think you have an answer? Oh, I think Natalie's gone. Okay, we have another Natalie. Okay, Ellie. Also, Ellie, we can't hear you. Okay. All right. So, okay, I'll stick with the crowd who's participating usually. Okay, let's see. So
I can say what I got.
Jessica, yes, thank you. Please tell me.
Yeah, so I got ti plus 1 minus 2 ti, this is for ti, the point ti, plus ti minus 1 over delta x squared.
Yes. We know how to do this. That's exactly, and a lot of heads nodding. Okay, that's exactly what this is. Okay, so you see how we converted now the second derivative into a discrete relation between neighboring points. So again, the way I'm thinking about this, I have this continuous equation, call it formula. It's not a formula, it's an equation. It's a differential equation. I can apply it at every point, but there's this annoying second derivative, okay? Think of it in another way. You have 100 points where you don't have for which you don't have a formula to get the answer. All you have is a second derivative. And you know then that you need, if those are 100 unknowns, then you need 100 equations. If there are 1,000 unknowns, you need 1,000 equations. Okay, excuse me. How do we build those equations? Okay, turns out the formula is, in this case, is the equation that we're gonna, is the equation at each point, and we're gonna put them all together and solve them together. And that formula is discretizing the second derivative. Okay, so now you see how we've built a relation at an arbitrary point I. Okay, we built a relation between ti minus 1, ti, and ti plus 1. Okay, now if you rearrange things a little bit, so we follow the strategy we followed for systems of equations, you put all the unknowns on the left-hand side and everything that you know on the right-hand side, you get this beautiful formula. Ti minus 1 minus 2 plus h delta x squared times ti plus ti plus 1 equal minus h delta x squared times t infinity. Okay, now this is the discrete governing equation at each and every point inside the entire domain. Okay, so now I'm going to ask you, we have all the ingredients to solve for the unknown quantities. In words, explain what we're going to do next. So like, tell me, how can I get t, how can I find the value, an actual value for t2, t3, t4, and so on? Like, what is the procedure we're going to do next? It's very simple. You don't have to even just the details. So in other words, I want you to see beyond this equation. So we have one equation at a representative point I. What are we going to do next?
Are you going to make a system of equations?
Yes, exactly. So this is a representative formula at every point. It doesn't quite give us ti because it depends on ti minus 1 and ti plus 1. So if we apply it at t2, is going to depend on T1 and T3. If we apply it at T3, it's going to depend on T2 and T4, right? But that's, at least it's a linear equation. And then if we put all of those together, we have enough equations as there are unknowns. And that, like Carl said, that is going to be a linear system of equations. Now, if you cannot see it yet, I want you to take a minute, okay, and write it down as follows. Write down the formula, this formula for T1, T2, T3, etc. Pay attention, however, that at T1, you have the value. So this equation doesn't really apply exactly at T1 because you have a given value at T1, okay? And same thing for Tn. So just write a few representative points, like do it for point 1, 2, 3, and maybe point n minus 1 and point n, okay? And then you should be able to see the system of equations. Excuse me. All right, any takers?
Can I try, Professor?
Go ahead.
So T naught minus 2 plus h delta x square whole T1 plus T2 equals negative h delta x square T infinity.
Okay, I'm gonna stop you there. So this is at what point is this equation?
T1.
Do you have it? Does anyone see a problem with what Sofit said? Okay, James, what is the problem?
Your T2 we don't have.
T2?
Yeah, we only know like T0 and which is known and T infinity which is also known. We don't know what T2 is.
No, but our goal is to find T2, right?
Oh yeah.
So does anyone see another problem? So our goal is to find T2, and then we're gonna write an equation at T2, and then write an equation at T3, and then we will have enough equations for all the unknowns, right? But what's another problem with what Sofit said?
We don't have a T0.
Yes, thank you, Porter. We don't have a T0, Sofit. Do you want a T0? Then you would have to write an equation at T0. But you'll always have one more unknown than there are equations, unfortunately. But even stepping back at 1, the equation is irrelevant at point 1, because you know the value of the temperature. Okay, so let me show you how I would do this. At point 1, T1 is simply equal to T left. Now remember, Sofit, we didn't define T0 when we set up the problem. There's no T0. So we started with T1 to Tn. You invented a T0. We're going to invent a T0 later when we talk about Newman boundary conditions, but right now we're not, okay? So T1 is T left. At point 2, you apply the equation, you get T1 minus 2, etc. T2 plus T3 equal minus h delta x squared, and then T2 minus, etc., T3 plus T4, and so on and so forth, all the way to point n, where Tn is equal to T right. Now, James, don't be dissuaded that, oh, we don't know T2 and we don't know T3. Well, of course we don't know them, but that's the goal. We want to find them. But now we have equations that contain all of those unknowns, T2, T3, T4, T5, etc. And we have enough equations, okay, to solve for all of those, right? We're going to have n minus 2, that we're going to have n equations by n unknown, for n unknowns, okay? However many unknowns you have, you're going to have this many equations, okay? And then when you see it this way, you can, if you haven't seen it yet, you should really review your linear algebra we did in the beginning of the semester, okay? It's not acceptable now that you cannot see this as a system of equations. And this is the system of equations. It's a system of linear equations, to be specific, right? And so now, do you remember this? Do you remember this structure? Tridiagonal system of equations. You know, this is how we got that. Remember early on, I told you, don't worry about how we got those equations. This is it. That's how we derive it. Okay, that's how we derive it. Now, all you need to do, once you do this, you typically do this by hand. You get this kind of generic formula. Bam. You just go and implement this in your code. Okay. And we did this at the beginning of the semester. Remember? Remember all of this. We did all of this. Okay. Now, we're going to try to do it again. Go ahead and download the boundary value problem example, heated rod with gaps from modules, from your modules. And we'll do this real quick. Okay, we're going to do a coding activity over here. Okay, so share the screen again with you. And okay, now continue focusing with me on Zoom. And I'm hoping you got your notebook up and running. So as usual, got the boilerplate ready for you over here. Give you a few more seconds to get the notebook. Anyone still working on getting the notebook? Okay. Run the basic matplotlib, etc. And then this is I'm showing you here the coefficient matrix. Okay. It has a tridiagonal structure. Main diagonal is mostly minus 2 plus delta x squared times h. Upper diagonal is all ones, except for the first point. Lower diagonal is all ones, except for the last point. Okay, that's why because of the boundary conditions. Okay. So in other words, the first equation is telling us simply T1 equal T left. Okay, it just doesn't do anything really. It just says T1 is equal to T left, and the last point says Tn is equal to T right. Okay, but all of the other points is just a system of equations, you know, that we're gonna solve. Okay. So now I got a bunch of things for you already ready over here. N is 200 points. We want to do it for 200 points. Now, be careful what you mean by whether you want to do points or intervals. Just be clear about that definition early on. Sometimes I use intervals, sometimes I use points. Okay, just make sure you understand you are clear about that. So let's do 200 points, rod length of 100. T left and T right are both at 300, let's say, and T infinity is at 500. Okay? So in other words, what's going to happen to the rod? What would you expect the temperature to look like? So we fixed T left and T right. Yeah. Okay. Abby's did this like a parabola, right? Exactly. Yep. Something like that. Because we are heating the rod with the air. T infinity is higher than the temperature at both ends, right? So while the temperature at both ends are trying to cool it, the air is trying to heat it. Okay. And the rate of heating is going to be dependent on this h, and cooling is going to depend on this coefficient h. Okay. And let's say this h is equal to 1. I put a lowercase h over here. Okay. Now the first step is to do a lim space for the rod. So let's go from 0 to L. Okay. But how many points? So this is going to give us delta x, right? So how many points would you put in here?
Would just be like n?
Will
just be n.
Okay. And then dx is simply the spacing between any 2 points in length space. Okay. That's your delta x. All right. So now the way we do this is we create a lower diagonal, main diagonal, and upper diagonal. Okay, what do we do for the lower diagonal? Come on. It's all ones, right? Except for the last. Yeah. And p dot 1 of size.
N minus 1?
And minus 1.
Yes.
Because
it's got one less number of points. Okay.
Now fix the end
end point.
So the last point on this lower diagonal is 0, right? So how do we do this? Come on, guys, you should know this.
Lower diagonal.
Last
entry is 0.
Okay. Create the main diagonal. It's minus 2 plus dx squared times h, okay, times np dot 1s of size n. Okay. And then we fix the first point and the last point of the diagonal, because the first one is 1 and the last one is 1. Okay. The upper diagonal is also mostly 1s, np dot 1s of size n minus 1. And you fix the end point, the first point in this case, its upper diagonal, 0, is equal to 0. Correct? I'm going to do 0.0, just to make sure Python's not going to parse them. Okay. So now you could use the Thomas algorithm or the tridiagonal algorithm or an iterative solver, but we're going to be using just a built-in Python routine. So we're going to need to build a dense system of equations or a full matrix. And remember, we used to do this with np.diagonal. We used to use that for verification purposes of our Thomas algorithm. Over here, we're just going to use that to solve the system of equations. It's a legitimate way. It's a little bit more expensive than the Thomas algorithm, but for one-dimensional problems, it's nothing. If you go to 3D problems and you use this, it's a very bad idea. Okay, so with np.diag, lower diagonal is located at minus 1, main diagonal is located at 0, and upper diagonal is located at plus 1. Finally, build the right-hand side. Okay, does anyone want to take this? So for the right-hand side, we got minus t infinity delta x squared times h, right? So this is going to be simply minus t infinity, what did we call t infinity? T inf, okay, times dx squared times h. But we still have to fix the first and last points to t left and t right. Okay? So what do? We just simply RHS 0 is t left, and RHS at the other endpoint is t right. Now solve the system of equations. Lim algebra.solve, coefficient matrix A, and right-hand side, and then you plot. Okay? What are we going to be plotting? We're going to be plotting on the x-axis, we're just going to be plotting x, the x location, and the solution. Okay? If you run this, you're going to get an error. Fix the left boundary, RHS0 is t left. Oops, I forgot to do an array here. That's np.1s of size n. Okay. Abby, you were right. Your intuition was right. Okay. Now, at the bottom here, I have another way of showing this data, where you can see how the heated rod looks like. Okay? That's cool. Right? Now you can play around to understand the physics. The value of H is going to be critical in determining how fast the heating is going to affect the distribution in the rod. Because that H contains two parameters, the heating from the air and how fast the temperature changes inside, how fast the temperature information is transmitted inside the rod. So there's two
heat transfer coefficients in there, H and K, H and lambda. Okay, you will learn this in your heat transfer. But the point is, if you play around with this H, so let's pick a very large value of H. Let's say 1,000, and run this. What's going to happen over here is that you have effectively dominated the entire rod with this heating through the air. Okay? The opposite is true. Okay? The opposite is true. If H is very, very small, the opposite is going to happen. Okay? Okay, hold on. There's a little header over here. One second. Okay, transfer H. Let's see. +3 equals so essentially, there's so here this is misleading. The color map. It looks like this, but pretty much there's actually this is not right. There's an issue over here because what I got here +3. Yeah. +3 to the power 2. So hold on. This is plots misleading us. Okay. So when the heat transfer coefficient is so small, the heating of the air has no effect on it. Look, it starts at 300, barely goes up to 302, and then goes back down to 300. Okay. If you keep decreasing this, okay, the plot is going to be misleading, but let me fix it for you. So if you do ELT dot Y P dot set ELT dot Y limit, if I do from 300 to let's do 300 let me see 300 to 350, what's going to happen? Well, sorry, 250 to 350. It's pretty much flat. There's no change in temperature because that heating of the air didn't do anything much. Okay, and you can play around with those numbers, but that's where once you write this down, then you can enjoy working on the physics, okay, and enjoy playing around with the different parameters to see what the physics are telling you. You could cool the rod, could go to 100, and then you get the opposite. Okay? Okay. Now we can switch back to Zoom and to YouTube and continue with our discussion. Any questions on the code? We've done this early in the semester. All that we've added here is how you derive the equations. Okay? And that's something that you're going to be responsible for. So on your final exam, I'll ask you, hey, this is the equation, discretize it, and give me the representative formula at a point in the domain. Trust me, you don't want to have to deal with that in your heat transfer class. Okay? Because they're just going to skim over that. Okay? All right. I'm gonna see you on YouTube.
Okay. Feel free to review what we did here, just for your own learning purposes as well. But the derivation, you need to understand that. Okay. I might change the equation a little bit. I might have a second derivative and a first derivative. You should be able to derive the system of equations just like we did here, okay? Okay, so we did all of that. All right, so now we're gonna take a step back and do some talk about some definitions. What we did here is solve a particular type of boundary value problems that had fixed boundary conditions on both ends. Those types of boundary conditions are called Dirichlet boundary conditions. And you essentially say, I'm gonna fix the value of the dependent variable, what I'm after, in other words, at the boundary. Okay, and that's called the Dirichlet boundary condition. Okay, now boundary conditions are important in boundary value problems by definition because they are boundary value problems. Excuse me. There's another very important type of boundary condition, and that's called the Newman boundary condition. And with the Newman boundary condition, instead of specifying the value of the dependent variable, you specify its slope or its rate of change. So again, we go back to rates of change. Sometimes you don't know the specific value of a quantity, but you know how fast or how slow it's changing. You know its rate of change, okay, gallons per minute, for example, right? So you know the rate of change. And it turns out that we need a mechanism to try to implement a boundary condition like this. And very simply, those are given by a first derivative at the boundary. So you define the slope of the variable phi. So instead of specifying the value of phi, you specify the slope of phi at the boundary. Okay, we're going to use beta to designate that slope just for simplicity. It's typically, for our intents and purposes, this will just be a fixed value specified by the user. Okay. For Newman boundary conditions, we have a little bit of a situation. Okay, because so although our equation is still valid, so we have ti minus 1 minus, at any point I, we have ti minus 1 minus 2 plus h delta x squared, ti plus 1 equal minus h. That's the same equation we're dealing with. It's still valid at discrete points. However, we need to do something different at the boundary. Because right now, previously at the boundary, we had t1 equal t left and tn equal t right. So that fixed the equation there. Right now, we only have t1 equal t left. But at the right boundary, we have dt by dx at n equal a beta. So that brought us back to a derivative rather than just an equation. So for Newman conditions, we need to discretize the governing equation at the boundary. We have to, because we don't have a fixed value. We have to assume that the equation is valid at the boundary, and we're going to go ahead and discretize it. Now, when we do this, you get Tn minus 1. This goes back to Sauvigne's point. Okay, so Sauvigne was right if we had a Newman boundary condition. Okay, so if we apply our discrete equation at point n, if you follow the nomenclature, you get Tn minus 1, Tn, and you get Tn plus 1. Okay, but we don't have Tn plus 1. Tn plus 1 doesn't exist. Okay, so we're going to assume that, okay, suppose that there is a point Tn plus 1. Suppose for a moment. We're never going to refer to Tn plus 1 ever again once we finish the derivation, but suppose for the sake of the argument that there is a fictitious point, we call this a ghost point in practice, called Tn plus 1. Suppose we are able to discretize this equation, okay, over there. So we get a Tn plus 1 here. The problem though is Tn plus 1, we need an equation now for Tn plus 1. Otherwise we will have more unknowns than there are equations. But then if we derive an equation for Tn plus 1 as a function of Tn plus 2, that keeps recreating the problem. So what we really need is to figure out a way to relate Tn plus 1 to all the points that we are concerned with. In other words, you know, maybe Tn minus 1 or Tn, etc. Okay? And we call that the elimination of the ghost point, or the elimination of this fictitious point. So what do we do here? We take the derivative that has been, we have one more piece of information, right, that we haven't used yet. So we use the first piece of information in that the equation is valid at all of those points. And the second piece of information is the fact that we know the slope of the temperature or the dependent variable at the boundary. So we're going to use this information to find a relation between Tn plus 1 and the points that we are concerned with solving. Remember, we are only trying to find equations for points 1 all the way to n. I don't want Tn plus 1. Okay, I want to eliminate Tn plus 1. So what do? Say you discretize the derivative as well, and we know how to do this. Okay, so you could use a backward difference. Okay, you could say Tn plus 1 minus Tn over delta x. The problem with that is that it's a first order approximation. And everything here is second order, but then you use first order here, that's going to destroy your global order of accuracy. It's a valid way of doing it, but be careful about that. A better way would be to use second order discretization for this derivative, which is Tn plus 1 minus Tn minus 1 over 2 delta x equal beta. Now see what happens. Now we have a formula relating Tn plus 1 to one of the points we are concerned with. we still don't know Tn minus 1, but we have an equation for it over here, right? So we have an equation, Tn minus 2 minus etc. times Tn minus 1 plus Tn. So we do have in the system of equations, Tn minus 1 is part of the solution, right? Tn plus 1 is not, but that's how we eliminate it. So you simply solve for Tn plus 1 and say Tn plus 1 is, 2 beta delta x plus Tn minus 1. And now you can take this Tn plus 1 and plug it up here. And then you have an equation that is not dependent on Tn plus 1 anymore. So in other words, the equation at this last point n becomes 2Tn minus 1 after you do the algebra minus, it's just standard algebra. You take Tn plus 1, plug it in here, collect the unknowns, and move everything that you know to the right-hand side. And this becomes your equation at the last point. In the previous case with the Dirichlet conditions, the equation at the last point was simply Tn equal T right. Right now with Newman boundary conditions, we only changed the last equation. It's 2Tn minus 1 minus 2 h delta x squared Tn equal all of this mess, okay? And now we have the entire system of equations. On the first point, T1 is equal to T left. Between 1 and n, you have the standard formula that we were dealing with. So between all of the points between, so from 2 to n minus 1, this is the equation. And then finally at the last point, at point n, you have that equation. It's because of the Newman condition. And then you have n equations and unknowns, and you can solve that as usual, okay? Now, in matrix form, always write in matrix form, it's easier. It looks like this. Again, we have the 2 plus h delta x squared everywhere on the main diagonal. Now, in the Dirichlet condition, we had 1 over here and 1 over here. Right now, we don't have 1 over here. For the lower diagonal, we have 1s everywhere except this entry, there's a 2. Okay? And up here, we have 1s everywhere except 0 over here, so this didn't change. And the right-hand side changed as well. T left, h delta x squared T infinity everywhere, and then the last point changed. Okay? Now it's still a tridiagonal system of equations. You can use the Thomas algorithm to solve it. Okay, but now we have the recipe. So Newman boundary conditions. They're a little bit trickier to implement, not to implement, to derive, but the implementation is very straightforward. Okay, so now with this system of equations, okay, we're going to go ahead and do the same problem we did. So go back to your code in the Jupyter Notebook and simply change to solve a problem with Newman boundary conditions. Okay, now I want you to enable the user to specify a value for beta, just like we specified a value for the number of points. I want to be able to specify a value of beta and see what happens. Okay, now this beta, or the slope of the temperature at the boundary, is going to tell you if the slope is negative, then you are withdrawing heat. If the slope is positive, you are providing heat. If the slope is 0, then no heat is being transferred. Okay, so this beta is that's the physical interpretation of beta. Now, depending on the other boundary on the left, the curves might be all over the place. Okay, and that's where you can play around with the parameters. Okay. I will see you on Zoom. We'll do the coding activity really briefly. I'll try to keep the slide shared so that you can do the implementation, okay?
All right, my pupils, I am back. I'm going to share my screen. My computer is churning like crazy. Okay, I'm going to share my screen. I'm going to move my slides over here next to this window. So I want you, now you got everything you need here, okay? I want you to change this code. Take your time. Change this code so that we are solving this system of equations, okay? Let me slide only. Let's remove this guy over here. Let's see. Do it fit slide? Slide. Can you see it? Can you see the slide? Okay. So go ahead and implement this. It's only a few points, a few things you need to change.
allow us to change the value of beta. Okay? Oops, that's too much. If I zoom in. Okay, this should be better for you. So really what you're changing from the previous problem is just the last equation, okay? It's just the last equation. That's the only thing you're changing from the last problem, from the previous problem. Go ahead, implement it, pick a value of beta, say, minus 100 or plus 100, see what happens. Any takers? So tell me what you're doing, where you're at.
I can share what I did.
Okay, do you want to guide me?
Yeah, so the first thing I changed is in the, let's see, the lower diagonal, instead of a 0 for the last point, it's 2.
Okay, correct.
The next thing is the main diagonal. I just did not change the last point because it's the same as all the other points. So I just took that part out. And then the upper diagonal is the same. And the right-hand side, I just changed, instead of changing the last point to t right, I changed it to that equation, which
minus
is
h.
Yeah.
Minus h delta x squared in t infinity, right?
Yep.
So minus h delta x squared t infinity, and then minus 2 beta delta x, correct? Times beta times delta x. Now we need to define beta somewhere, so let's do beta, say, equal minus 100. And that's it. That's it. Let's run this and look at that. The temperature on the right now could be anything. We haven't fixed it. We only fixed the slope. Now you better be sure that the slope at the last point is equal to beta. So in our case, we said beta is what, minus 100.
indeed, our slope is negative over there. It's 100, minus 100, okay? So let's say beta is 100. Oops. Yeah, my spinning wheel of fortune, because my computer is really acting up with everything that's going on. Sorry about that. So change the value for beta and see what happens. Okay, put it like 100. I don't know why this is throwing a fit. Looks like Safari is having problems. So change the value to 0. Then you should expect the slope on the right to be 0, right? So you're going to have a curve that's going to dip or go up and then dip all the way to 0, right? It's going to be parallel with the x-axis. Let me restart my Safari. Can't even restart it. Okay, I apologize about that. Something is going on with my computer over here. Okay, I'm going to stop the share. Oh, looks like everything is locked up now. Cannot even stop the share. Okay. All right, let me try. Oh, okay, it's back. It's back. It was like doing something. Okay. All right, so if we go back, if we put beta equals 0 and run it, and then you plot it, see how the curve goes down to 0. I'm not sharing anymore. Okay, I'm not sharing. Looks like I'm not sharing. Okay, see how the curve goes back to 0. So that's how you check your implementation makes sense. Okay, that's how you check that your implementation makes sense. See over here, it's 0. The slope is 0. Okay, you can change your slope. The beta, let's do 1,000, you know. Then look at that. It's actually a very high temperature on the right-hand side because you're supplying a lot of heat, right? The slope is positive. You're putting a lot of heat coming in, okay? Anyway, that's what this is, Newman boundary conditions, okay? Let's switch back to YouTube. We're practically done with boundary value problems. There's still a couple of issues with boundary values that we're going to discuss between today and Thursday, okay? I'm going to get slightly started on those. And let me see. Navigator. Okay. Actually, I think we will do the following example together, and then I'll call it a day for today's lecture. Okay. Still having issues now. Now Keynote is throwing a fit. That's really bad. Okay. Hold on a minute. I'm just restarting my Keynote. Okay, guys, I don't know what's going on with my computer, but I can't even get my slides up and running, unfortunately, which makes me think that I need another computer now, a bigger and better computer. Okay, first quit. Let's see. Okay. All right, open recent ODEs. Okay, so I'll finish this on Zoom because there are a sequence of activities that we're gonna need to do together. Okay, play slideshow in window. All right. Okay. Okay, so we are continuing on Zoom. Okay, can you see my slides? Okay, great. We did this problem, you know, in the code together. Now we're going to continue with an example. Okay, the next step is going to be an example. So now I'm going to take a different differential equation, d2u by dx squared equal x squared u. So I changed here the dependent variable from phi, from t to u. I called it u. So d2u by dx squared equal x squared u. And now on the left, I have a Newman boundary on the left, du by dx equal alpha at x equals 0. And on the right, I have a fixed boundary, u at x equal L. I say it's equal to UL or beta. It's a fixed value, okay, at the right-hand side. So there's a little typo over here that is showing that UN equal beta. It's actually equal to U at L, okay? It's actually at the right-hand side over here, okay? So this should be U at L is equal, let's say, beta, okay? And therefore, you know that UN is equal to beta, okay? So you know this, all right. Okay, great. So now the first question I have for you is, at an interior point I, write the discretized equation. Don't worry about the boundaries yet. Just at an interior point, discretize this equation. d2u by dx squared equal x squared u. Remember that the second derivative is ui minus 1 minus 2ui plus ui plus 1 over delta x squared, okay? All right. Sean, do you
Yes.
want to take this, or you want a few more seconds?
I think I got it. I think I have something. So it would be doing a finite differencing method for replacing the second derivative.
Mm-hmm.
And so it'd be u of I minus 1 minus 2ui plus ui plus 1 over delta x squared equals xi squared ui.
Correct. Okay. So you just simply apply the finite difference formula on the second derivative. Now notice on the right-hand side, everything is at point I, okay, is evaluated at point I. Now you always rearrange things a little bit so that you put unknowns on the left-hand side and what you know on the right-hand side. It just so happens that everything on the right-hand side in this case is equal to 0. Okay, now give me the formula. What do we do at the left boundary? So now discretize the governing equation, okay? So the d2u by dx squared, etc., and assume there's a ghost point at 0. So there's a ghost point u0, okay? So that's almost what Sovit did earlier. Maybe Sovit, you take this.
So this is going to be the same, right? So u of 0 minus 2 plus xi square ui.
Xi, what is I in this case? This is at point 1. Should be
So it is
x1.
going to be. Yeah, I'm kind of confused myself right now. So.
Okay.
So now we have 0, right? So
it's u0 minus 2 plus delta x squared, x1 squared, all multiplied by u1 plus u2 equals 0. Remember, always at the boundaries, the equations are going to be different. So you have to write the full equation, okay, at the boundary. So now at the left boundary, because we have a Newman condition, we decided to have this fictitious ghost point at u0, okay? But remember, you're applying the equation at point 1. So that's what tells you have x1, not xi. If you put xi, you know, it's not going to work, okay? There's no x. What is I? I is equal to 1 in this case. So now go ahead and eliminate u0 by discretizing the boundary, the Newman condition, okay? So Newman condition is du by dx equal alpha, okay? Adriana, would you like to take this? Take your time.
Okay, so I think I have it down. Just kind of using the same method that we did for the beta. So using like the difference formula, it would be like u1 minus u0, and then divided by 2 delta x, right?
Okay, so you did the backward difference formula, which is first order, and it shouldn't be over 2 delta x, it should be over delta x, right? Because it's the spacing between u and u0. So you had a mistake there. I would recommend you to, so that's a legitimate formula. It still allows you to eliminate u0, but it gives you a first order approximation. So I would recommend you do a centered difference, which is u2 minus u0 over the spacing between those 2 points, which is 2 delta x. Okay? And that's what I would recommend, is you do u2 minus u0 over 2 delta x equal alpha. So that gives you u0. Now you plug u0 back into, Sarah, is this clear? I saw you squinted for a second there, and okay. And then yes, you got it? Okay. And then you put u0 back in the equation at this first point on the left where the Newman condition is, and that gives you the updated equation at that point. You arrange things and you see how it changes your equation. And then finally at point n, un is equal to beta, and you're good to go there, okay? And that gives you the system of equations in matrix vector form. So make sure you rehearse this at home, okay? Make sure you can rehearse this at home and can produce this system of equations, okay? And this would be it for today. We covered essentially linear boundary value problems. We still have one thing to cover with boundary value problems, and those are going to be nonlinear boundary value problems, okay? That's kind of the, you know, potentially most complex type of boundary value problems you will deal with. Now, be careful. I might ask you here to do d2u by dx squared plus du by dx equal x squared u. And you should be able to discretize that equation and come up with a system of equations at each and every point, okay? Because you know how to do finite difference, you know how to go from a continuous derivative to a discrete derivative and relate the points with each other, okay? That will be it for today. Thank you for your attention. And